Good afternoon, or yeah, good evening, everyone. This lecture is 3.11 about hyperbolic functions. So it's probably something you haven't heard of. You've seen the button on your calculator, and you'll see why in a second. But what are hyperbolic functions? It's just even and odd combinations of the exponential functions e to the x and e to the negative x. So what do we mean by combinations of e to the x and e to the negative x? These are both exponential functions, right? Because the x's are in the exponent, they're not at the base level. So if we look at this right here, this is an example of a hyperbolic function. It's associated with some kind of trig function. If you notice, we have, if I block the h out, we have sine of x. But whenever you see an h in there, that means the hyperbolic sine. Or if you had cosh, like cosh, that would mean the hyperbolic cosine, like that. Or if you had tan hx, hyperbolic tangent, and so on. Now, algebraically, these can be expressed as, like if we look at this one, hyperbolic sine, e to the x minus e to the negative x over 2. And for cosh of x, or hyperbolic cosine of cosine, we have something very similar, but it's just positive right here. Now, do you need to remember these right here? No. Okay, this is just how they're expressed algebraically with the exponential functions. The important thing to remember is the derivatives of these things right here. I'm going to go over that in a second. All right. And these have some identities, like how you had sine squared plus cosine squared equals 1, for example. You also have, for hyperbolics, you have similar identities. Okay, like we have cosh squared of x, or hyperbolic cosine of x, minus hyperbolic sine of x, and that's equal to 1. So remember, sine squared plus cosine squared was 1, but with the hyperbolics, if it's cosh squared minus sinh squared, you get 1, okay? You can also have 1 minus hyperbolic tangent squared of x, and that's equal to the secant, or hyperbolic secant squared of x. These are just, again, identities right here. We'll call them like hyperbolic Now, do you need to remember these? No, again, because normally through your math careers or engineering careers, you're going to be using sine, cosine, and tangent mainly. So those, like the sine squared plus cosine squared equals 1, or 1 minus tan squared equals secant squared, that's another identity that you need to remember. You probably should commit to memory. But these right here, not really. Same thing with the derivatives, okay? With the derivatives, you just have to know how to apply the formula. Just like with the derivative of the inverse trig functions, you don't need to memorize them. You just need to know how to apply them. And I will supply those to you on the test, okay? Like when you look at the instructions on the test on Canvas, you'll notice I put when it comes time to take that test this upcoming Monday, right? Not the 21st, but the 28th, you'll see all those derivatives, like the derivatives of the inverse trig functions, the derivatives of the hyperbolic functions, okay? Those will be located in the instruction part of your test, all right? You just have to know how to use them. Let's just make a list, okay? Derivatives of hyperbolic functions. And you can always Google all this stuff too, right? Like derivative of trig functions, derivative of inverse trig functions, derivative of hyperbolic functions, and do like a Google image search of it. And all this stuff will always pop up right there. But if we have like du of hyperbolic cosine of u, what is that right there? Well, it's very similar to the derivative of sine, right? What's the derivative of sine? Cosine. This one behaves the same way. It's just hyperbolic cosine of u, but then we have times du dx. It should be an x right here. Change this to an x. So you see we have to chain it, right? It's the chain rule every single time. Like you do it forever and ever and ever. You derive the outside part, you leave the inside alone, and then you derive the inside. Then if we have ddx of hyperbolic cosine of u, well, that one is very similar to cosine. Remember, the derivative of cosine of x was negative sine of x. The derivative of hyperbolic cosine is actually positive hyperbolic sine of u in this case. So no negative sign right here. And it's still times du dx. Chain rule, right? You got to derive the inside as well. We also have ddx of hyperbolic tangent. That one is just equal to secant squared, or hyperbolic secant squared of u, and then du dx. That's the exact same derivative of tangent, right? Derivative of tangent is secant squared. So you're noticing how the derivatives of these hyperbolics are very similar to the derivatives of the regular trig functions. Then if we had the derivative of the cosecant or hyperbolic cosecant of u, like that, that is negative cosecant or hyperbolic cosecant of u, and hyperbolic cotangent of u, and then times du dx. So usually the cosecant, secant, and cotangents were a little longer than these first three right here. Again, what are we doing? Deriving the outside, keeping the inside alone, and then last step is you got to chain the inside, right? Then we have two more. The derivative of hyperbolic secant of u. Very similar to the derivative of secant. Remember, the derivative of secant was secant x tan x. This one's going to be very similar. It's just going to be negative instead. So we're going to have negative hyperbolic secant of u, tan hyperbolic tangent of u, and then of course chain rule right here. And then our last one, ddx of, what do we need? Cotangent, hyperbolic cotangent. So what's that one going to be? That's going to be negative hyperbolic cosecant squared of u, and then of course times the derivative of the inside. So those are the 6 right there. Again, you don't need to memorize these. You just have to know how to apply them. All right. You will be given these formulas in the instruction part of your test 3 that's coming up Monday, September 28th. Now, let us go out here and try to find the derivative of some of these. Like, let's say we have f of x equals hyperbolic sine of 2x cubed, for example. And we want to do that. So remember, the derivative of hyperbolic cosine was hyperbolic cosecant, right? So what do we need to do? Chain rule it. Derive the outside portion. That's just hyperbolic cosine of 2x cubed. Then we have to derive the inside, right? So what's the derivative of 2x cubed? It is 6x squared. So your derivative is just 6x squared, and then hyperbolic cosine of 2x cubed, like that. So very similar to how we were doing trig functions, right? It's just now you have an h right here slapped inside of, or slapped next to all the trig functions. What if we had f of x equals cosh of ln of 2x? So this is still a chain rule, right? We're actually going to do the chain rule 3 times. Right here, we're going to do it twice. Once on the outside and once on the inside. This we have 3, right? I put 3 different marker colors. 1, 2, 3 right here. How do you start that, right? How do you derive with the chain rule? You always derive from the outside and you work your way in. So first we need to take the derivative of hyperbolic cosine. What is that? It's positive hyperbolic sine. So it's sine of 8 or sine h, sinh. And remember, nothing else changes, right? This is still ln. And then we have of 2x. Now we're done with the outside. We move to the internal piece. Now we need to take the derivative of ln of 2x. What's the derivative of ln of 2x? Remember, the derivative for logs, natural logs, is 1 over the stuff. And then times the derivative of this piece right here. So times the derivative of 2x is 2. So that's your whole entire derivative. So what is that? Let's, clean it up a little bit. Well, we're going to move the constants out in the front, right? Like this is, I'm going to take this and put it out in the front because we have normally constants, then algebraic terms, then trig terms, right? So this is just 2 over ln of 2x hyperbolic sine of the natural log of 2x. That is your answer right there. What if we had like f of x equals natural log of the hyperbolic cotangent of x squared? So again, chain rule 3 times, just like this one, right? It's just natural logs on the outside. Guess what? You still work it out the same way. So how do we do that, right? Well, we start with the outside. The derivative of natural log of whatever, remember, is 1 over whatever times the derivative of whatever. So we have 1 over all this, right? We still have our cotangent, our hyperbolic cotangent of x squared. But now we need to derive this inner piece, right? What's the derivative of hyperbolic cotangent? Well, if we go back and we look at, what we just wrote down, the formulas, the derivative of hyperbolic cotangent is negative hyperbolic cosecant of u. Oops. U in this case was x squared. And then also, well, that's it. And then times the derivative of the inside, or the blue piece, which is 2x. So again, we had to derive first the ln component, right? So that's 1 over the stuff times the derivative of all this stuff right here. I'll put this in red. So the derivative of the stuff in this case, right, we had 1 over the stuff times the derivative of the stuff. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared of x squared in this case. But then we had to chain it one more time, right? We had to sit there and take the derivative of the inside, which is 2x. And the final answer is 2x over the hyperbolic cotangent of x squared. And I'm going to move that negative sign out in the front. And then we still have the hyperbolic cosecant squared of x squared. So I took this, moved it out front, negative out front. This stayed on the bottom. This I just brought along in the numerator. What if we had y equals, say, 5x squared, and we wanted to do 5x squared secant, hyperbolic secant of x cubed minus 1, something like that, and we want to find y prime. How do we do that right there? Or multiplying two different terms, right? We have an algebraic thing times a hyperbolic trig thing. What should that tell you? Oh, I have to do the product. Got to do the product rule. So this is F and this is G right here, right? So we have to do our good old FG prime plus GF prime. So F times G prime. Well, F is just 5x squared. What's the derivative of G in this case, or the derivative of hyperbolic secant of this stuff? The derivative, remember, of hyperbolic secant is negative secant, hyperbolic secant of the stuff, and also tangent, hyperbolic tangent of the stuff. But remember, we have to chain this, right? So if we were just taking the derivative of secant, hyperbolic secant, remember it's negative secant tangent of that stuff times the derivative of the inside. So we have to derive the x cubed minus 1. What is the derivative of x cubed minus 1? It's 3x squared. And then the derivative of a constant is just 0. So this whole thing here, all this is your G prime. And then we still have to do plus GF prime. G was hyperbolic secant of x cubed minus 1. And the derivative of F is 10x to the first, right? It's a lot easier to do. And then to finish it up, we can just clean it up, right? Like we can move this stuff out in the front. Like I can say 3x squared times 5x squared. That is 15x to the fourth. And we can move this negative out in the front. And then we're left with hyperbolic secant of x cubed minus 1. And then hyperbolic tangent of x cubed minus 1 plus 10x hyperbolic secant of x cubed minus 1. So when you're working these, remember, take your time with it, right? It's a lot of little letters, right? A lot of little signs that can pop out of there. Again, you just have to know how to apply these formulas. But the part that people mess up on is they'll forget, oh, to multiply, you know, this and this, or they'll forget the negative that pops out of that formula. Don't get this formula wrong right here, right? You have it in front of you. So just watch the signs. And especially with the derivative of secant, for example, remember secant, when you derive it, whether it's secant or hyperbolic secant, it's always going to blow up into a secant tangent of something. Whatever that something is, make sure you put it, you know, you apply both the secant component and the tangent component to that U piece right there. Don't just do it for one and then forget it for the other, right? Like you have to include that. And of course, chain rule every single time. Where is this 3x squared coming from? It's because after we derived hyperbolic secant, we had to derive the inside, right? The derivative of x cubed minus 1 is 3x squared. Now, let's say we have y equals e to the, I'll say, I'll say e to the hyperbolic tangent of 2x. And we want y prime. How do we take the derivative of e to whatever? Remember, if we have y equals e to the u, dy dx was equal to e to the u times du dx, right? So the derivative of e to whatever is e to whatever times the derivative of whatever. This you need to memorize, right? This is not going to be given to you. Again, I will only give you the formulas for the derivatives of inverse trig functions, derivatives of the hyperbolics, and the geometric shapes, like the volume stuff, you know, for the related rate problems like that. Volume formulas specifically, like cone, things like that. So coming back to this, if we need to derive e to the tangent, hyperbolic tangent, we want to do that. Slap an h in right here. Hyperbolic tangent of 2x, okay? Make sure you put the h. How do we do that? We just follow this, right? Derivative of e to whatever is e to whatever times the derivative of whatever. So right here we have e to whatever. That's e to the hyperbolic tangent of 2x. And then we go times. We have to derive this piece right here. What's the derivative of hyperbolic tangent of 2x? Well, let's start from here, right? What's the derivative of hyperbolic tangent? It is secant, hyperbolic secant, hyperbolic secant squared, right, of 2x. And then we have to derive the inside of that, right? Continue training, and we get times 2 because the derivative of 2x is 2. So what does that leave us with? We have y prime equals 2, and then e to the hyperbolic tangent of 2x, and then hyperbolic secant squared of 2x. And there's your final answer. So these problems aren't too bad, right? When you follow the formula, just make sure you follow it correctly, right? And please don't forget the chain rule. That's what throws off a lot of people is they'll derive this part, but then they'll always forget to derive the inside of the trig function. You got to do that, right? You have to always remember, oh yeah, I need to lastly derive what's on the inside of the trig function. So this is 3.11. Again, I will supply the formulas for this, the derivatives of the inverse trig functions, the derivatives of the hyperbolic functions on the test. You just have to know how to use them, okay? So that is it.